Yes. And we're off. All right. Number 1, 14.2 practice problems. There are 2 major types of problems that you guys are going to see. There are combined gas law and there's ideal gas law. Well, sort of. Just watch.
It'll be online.
We'll see if I'm satisfied with how it looks.
Okay, cool.
Okay. Here's the deal. Combined gas law. Combined gas law deals with changes or changing conditions. Okay. The ideal gas law. Get my mess out of the way here. The ideal gas law deals with status. Okay, you guys talking right now is really bothering me. The ideal gas law deals with the status of a gas. Okay, so let's look at the 2 equations. We've got combined gas law is P1 V1 over T1 equals P2 V2 over T2 for a certain amount of gas. So in other words, this is measuring how your gas is changing from one set of conditions to another set of conditions. Can you guys see that? We have a starting set and a finishing set. Okay. Ideal gas law is how it's just, this is how the gas is. How much do you have? What temperature is it at under all of these other conditions? Does that make sense? There's no initial condition, final condition for the ideal gas law. It's just, this is your pressure, this is your volume, find the number of moles if you have this and this. Or it's just establishing what the condition is, what the gas is like right now. So most of these on 14.2 are dealing with a change in condition. So what we're going to do is we're going to look at these guys over here. We've got we're going to go through and label all of the things that we know from this problem. So for number 1, what things do we know? We've got a volume of 458 at a pressure of 101 and a temperature of 295. Okay. Then, when the pressure is changed, okay, so when it's changed, there's our change, that's going to establish a new set of conditions, right? Okay, so what we want to do is find out what our initial set are and what our final set are. So we're going to start with P1, V1, and T1. What are we starting with? Well, our P1, our initial pressure, was right here, 1.01 kilopascals. Okay, so we can even call this okay, so come over here, we can even call this V1. I'm sorry, that's P1. Oops. That's P1. This up here is going to be V1. This is where we start. So V1 is going to be 458 milliliters. And then T1 is going to, oh, I should not write on my slate with my pen. That would be bad. Okay, and T1 would be 295K. Okay, so then P2 and V2 and T2, we need to find those because those are our after conditions. So P2, it says when the pressure is changed, the volume becomes 477 milliliters. If there has been no change in temperature, what is the new pressure? So which one of these things are we looking for? We're looking for the new pressure. Good. So we don't know what that is. Okay. We do know, however, that V2 becomes 477. This is V2. That's 477 milliliters. And then temperature says there's no change in temperature. So it's going to be 295 Kelvin. Same temperature, right? Okay, so now that we're done looking at Taylor's funny face, that's right. It's going to be on YouTube and everything. Okay. In fact, we'll do a tag, plus Taylor's funny face. Okay, so we're looking for P2. So we're going to need to solve P1, V1, T1 over P2, V2 over T2 for which one? For P2. Okay, there's a trick though. Notice how these two are equal to each other, right? That means that we can actually cancel them. So P1 V1 over T1 equals P2 V2 over T2, but since T1 equals T2, they can cancel each other, leaving you with P1 V1 equals P2 V2, which is the equation for, anyone? Boyle's Law, there you go. Because they're equal to each other.
Okay.
So there's no change there, they have no effect on the situation. Okay? So we're solving for P2, so we're going to divide by V2, right? Divide by V2 to get P2 by itself. And then we plug everything in. So P2 is then going to equal P1 V1 all over V2. Okay. Then we bust out the calculator. Oh yes, we bust out the calculator. And we get 1.01 times 458 divided by 477, and that equals P2 equals 0.970 kilopascals. And that's that. Got it? Okay, don't put 0.97. Put 0.970. All three of these had three significant figures. This right here, 0.969, rounds to 0.970 to three significant figures. Yeah? You guys see that? You have to include the zero. Okay. So, let's look at a different one. No, all of these are PV over T's. So, I want to do a ideal gas law. Yeah, that's not it. Okay, that's 14.2. Okay, it's going to be 14.3 then. Okay, so now flip through the pages, and now we're going to do 14.3. And there's number one. Ideal gas law. Now this next one is a situation where it's just asking you for the situation of the gas. This question states, what volume What volume would be occupied by 100 grams of oxygen gas at a pressure and a temperature? So what stuff do we have? We know that there's a pressure. We know there's a volume. We don't know what it is, but that is something we're going to have to find. We have some amount of gas, and for our purposes, N is our amount of gas, and then we also know a T. Okay, so what do we know for our pressure? We know our pressure is 1.50 atmospheres. Here's our pressure here. Okay, our volume, we don't know. That's what it's asking for. N, well, the amount of gas we have is 100 grams. Still to three significant figures. We are capable of figuring out our number of moles from our grams of oxygen. We'll get to that back in a sec. And our temperature is 25 degrees Celsius. Okay, that should also send off a red flag. Woo! Celsius, Celsius, we don't like Celsius. We've got to convert to Kelvin. So this is 298 Kelvin. Alright, so let's get to our grams of oxygen gas. We're on Graham Island, we need to convert to moles, so we're going to divide by 1 mole of O2 is 32 grams of O2. How do we know it's O2? Because oxygen is one of the Magnificent Seven. And we've learned that over the last 7 months, because... Oh, yeah. Yeah. What's that? 32 grams. I'll write this bigger. So, 100 grams of O2 times 1 mole of O2 over... And that's going to be about 3.125? 3.13 moles. 3 sig figs. Come on, Ahmad. Alright. That's shoddy work you're doing. Alright. Okay, so do we have questions on how we found the number of moles? You are going to be expected to do this. To find the number of moles of the gas, or to find the grams of gas that you have based on your number of moles. The moles don't go away just because we're out of stoichiometry. Okay. So now we have pressure, we've got number of moles, we have temperature. There's something missing though. No, there's something else missing. The ideal gas law one of these things is not like the other one. We don't have R.
0.8 something.
This is 0.08 something. Atmospheres, liters, mole, Kelvin. Okay. Now gosh darn it, if you don't write the whole thing out, okay, I'm going to start marking you down. What's that?
The atmospheres times liters.
Atmospheres times liters divided by mole times Kelvin. Okay, this exists. Okay, so we've got the 4 things. We've got pressure, we've got number of moles, we've got our temperature, and we have R. R. So we are looking for volume. To solve for volume, volume is going to be solving for volume, we're going to get nRT over P. Then we plug everything in. 3.13 mole. 0.0821 liters, atmospheres, mole, Kelvin. Times 298 K off the side. Divided by 1.5 atmospheres. Stop! Whatever you guys are doing, whatever the giggling is going on, knock it off. Thank you. Oh, I thought I paused it. I guess not. Too tough to edit out. I'll leave it in there. Knock it off. Alright. So our volume here is all those things on the top divided by that on the bottom. Let's bust out our handy dandy calculator again. And we get 3.13 times 0.0821 times 298 divided by 1.5, and that equals
No, you did the one you said. You put the 0.081.
it just did 0.082.
Yeah.
Okay. Volume equals 51.1. Ooh, what is that going to be? That should be liters, yeah. Okay. At this point I want to talk about checking answers and making sure things make sense. What do we know, in general, what do we know about liters and moles? The 1 mole of gas is going to equal how many liters? 22.4, right? So take a look at the problem right here and estimate, or actually just see, does this make sense? Okay, we're at an increased pressure right here, but at the same time we've also got 3 moles of gas. So it should make sense that it's going to be significantly more than 22.4, right? 3-ish times 22.4, that would be 67, okay? But that's a 1.5 atmosphere, so it's going to be like 2/3 of that. That makes sense? Okay, so this value should make sense to you guys. Should be okay. If we got something like 5.2 liters, that should ring bells. Like, okay, that doesn't feel like enough because we've got a whole lot of moles over here. We have a whole lot of moles for our volume. Okay, so that was number 1 for combined gas law. This was number 1 for ideal gas law. I will set you guys off to work on your own, and if you have any questions, let me know.